Alright guys, so just a moment ago I was going through Lewis acids and I'm gonna explain what I learned, okay? So yeah, let's go right up to Lewis acids first. So there are 5 categories of Lewis acids, and let me start from category 1. So all cations are gonna be Lewis acids, be it sodium ion or what's that? That's lead, okay? Pb, lead ion or copper ion. They are all gonna act as Lewis acids because they have the tendency to accept a pair of electron. So sodium, that's a normal cation. Lead is also a normal cation because these guys are from S and P block, while this copper, uh, that's from D block, and it's called pseudo noble gas configuration cation. So cations from D and F block, they are called pseudo noble gas configuration cations. Okay, so that's the first category of Lewis acids. Now the second category are the elements of group 16. Wait a second, I gotta show you the periodic table where actually sodium, lead and copper are situated. So where's sodium? Where's sodium? Oh my god. Okay, that's sodium, alkali metal. So that's in S block, and lead, that is in P block, and copper, that is in D block. Okay, so yeah, elements of group 16. Now the elements of group 16, they have only 6 electrons in their valence shell. That means they will need one pair of electron to complete their octet state. So they are going to act as Lewis acids. Let me show you group 16 real quick. That's group 16, and they will need 2 more electrons to fulfill their octet state. So all these elements, oxygen, sulfur, selenium, tellurium and polonium, they are going to act as Lewis acids. Okay, so yeah, the next category is of the electron deficient compounds. BeCl2, B2H6, or you could call it boron hydride. It is actually BH3, but since it's a dimer, it's diboron. It exists as a dimer. BH3, it exists as a dimer, so we write B2H6, and that's diboron, and BCl3, boron trichloride. These are all electron deficient compounds, so they are going to act as Lewis acids. Let me just explain that right here. So that's boron. It has like 3 electrons in its valence shell. Yeah, 1 2 3. So when it forms a covalent bond with chlorine, it will have at least 6 electrons in its valence shell, which is 2 less than the octet. Okay, so it has the tendency to accept a pair of electron. So boron trichloride will also act as Lewis acid. All these compounds, they are Lewis acids because they are electron deficient compounds. And the fourth category is of the molecules which have multiple double bond between the elements of different electronegativity. The best example here would be carbon dioxide. Carbon dioxide as a whole, it's a non-polar molecule because these dipole moments, they cancel each other. Oxygen is more electronegative than carbon, no problem with that, but these dipole moments, they cancel each other. Although they cancel each other, there's a partial positive charge on this carbon right here, so that will accept a pair of electron, and that's going to act as Lewis acid. Next category is of the molecules having back-end d orbitals at central atoms. So how that works, take a look at carbon tetrachloride and SiCl4. Carbon tetrachloride is not a Lewis acid, but SiCl4 is. Both of them, carbon and silicon, they have 4 electrons in their valence shell. But the core here is that silicon, it has a back-end d orbital. So let me show you that really quick on the periodic table. So where's my carbon? It's right here. Carbon, it has how many electrons? 4 electrons on the valence shell, group 4a. So it has 4 electrons on the valence shell. That's gonna form 4 covalent bonds with chlorine, and it will have 8 electrons in the valence shell. No problem, it's fulfilled. And you see that there's no vacant d orbital, 2s2 2p2, so no chance of having a d orbital there with carbon. But silicon, on the other hand, it has a vacant d orbital because it belongs to group 3. Oh, that's period, okay? So it belongs to the third period, and 1s, 2s, 2p, 3s, 3p, 3d. So it will have a vacant 3d orbital, so silicon will act as a Lewis acid. Same goes with SnCl4. SnCl4 tin tetrachloride, that's also gonna be a Lewis acid. So that's all about the Lewis acids there. Now what about the Lewis bases? Lewis bases are exactly the opposite of Lewis acids. These are the stuffs that have the tendency to donate an electron pair. And you probably know that Lewis acids are electrophiles and Lewis bases, they are nucleophiles. So what are Lewis bases? All the anions and the molecules which have a lone pair of electron. For example, water, the central oxygen atom in water, it has two lone pair of electrons. It can actually donate this one. Same goes with ammonia. Ammonia is also Lewis base, or you call it nucleophile. So guys, that's all about Lewis acids and Lewis bases.